Hello, everyone. My name is Eugene Goldstein, and I have been honored to present 4 lectures on the geometric design of major urban roads as part of your transport systems course. The aim of the lectures is to provide you with the theoretical background to geometric design of major urban roads and provide an overview of a performance-based road geometric design process. As part of the lectures, you will learn about the fundamental design considerations, design inputs that would need to be used to develop the geometric design, the geometric design principles related to horizontal and vertical geometry, road cross-sections elements, and the road safety. The information that I would provide during the lectures should be only used as a guidelines. In practice, the guidelines must be applied sensibly and flexibly in conjunction with your skills and judgment as a potential designer. As a designer, you should have regard for particular circumstances in each case, including the importance of the road under your design, the nature and amount of traffic expected to use it now and in the future, and the cost and implications of the alternatives. Compliance with the guidelines does not relieve you of responsibility for establishing that your design was suitable, appropriate, and adequate for the purpose stated in the client's project requirements. In selecting design criteria, you should take care to ensure that the selection of a minimum criteria does not lead to an unsatisfactory or unsafe design overall. On major urban roads, the expectations of drivers are normally for a high standards facility. You as a designer should remember that consistent selection and application of design standards over a reasonable length of road is desirable, and a consistent and appropriate signing and delineation can compensate to some extent where less than desirable geometric standards are unavoidable. However, the use of signage and the line marking should not be seen as a substitute for safe geometric design. Prior to designing major urban roads, I would be very keen for you to familiarize with a glossary of terms used in the road and traffic engineering practice. For these purposes, the Australian standards AS 1358/2002 is probably the most suitable document. It will provide you with an alphabetical list of terms in road and traffic engineering. For example, road, roadway, a route trafficable by motor vehicles in law, the public right of way between boundaries of adjoining property. Freeway or expressway. In Victoria, we're using the term freeway. In New South Wales and Queensland, they have got tendency to use the term expressways. There's no difference. The fundamentals are the same. A divided highway for a through traffic with a full or partial control of access, and generally with great separations and intersections. In other words, it's a roadway that would allow a free traffic flow. Overpass. Some of you may recognize this overpass, some of you may not. It's actually, picture has been taken about 19 years ago, not about, it's 19 years ago. And it's Collins Street extension. To the right, these days, you may see the Southern Cross Station, and to the left, the H headquarter, and both to the right and left, these days there is a high-rise buildings, and the extension is actually taking closer to further down to the waterfront. What is the overpass? It's a grade separation where the subject carriageway passes over an intersecting carriageway or a railway. In this particular instance, if you're familiar with the area, and you can see actually in the photograph, it's actually crossing a range. I can give you the exact number, 11 railway lines. Viaduct. A long bridge composed of a series of spans, usually of land. Bridge rotary interchange. An interchange between a freeway, an expressway, and a surface road or roads in which the ramp terminals connect to a roundabout, which is grade separated from the freeway or expressway. Typically, you would see this type of structures on the approaches to the large cities. It is highly unlikely you will see this type of structures within the cities. It requires a lot of land, and land, as you're probably well aware, within the cities are quite expensive. Elevated roundabouts, it's a quite interesting structure, quite rarely where it can be used, but obviously based on the client's requirements, there is a room to imagination, and structural engineers exercise their intelligence to come up with a very impressive structure. Charles Grimes Bridge, that structure has been built, designed and built not far away from the Collins Street, crossing Yarra River. For those who know the area, the picture has been taken about 20 years ago. Okay, there is a new complex of a DFO Southern Wharf Shopping Centre. Now, the purpose of this picture is actually to demonstrate to you, by gaining knowledge, by learning about the fundamentals of the geometric design of major roads, by familiarizing yourself with standards and the guidelines, you can design this type of this sort of wonderful structures. One of the main sources of the knowledge, okay, other than my lectures, okay, and my notes, you can use the available standards and the guidelines. The most suitable standard, or the guideline rather than the standard, is the Guide to Road Design, part number 3, Geometric Design, prepared by Austroads. Okay, this document provides road designers and other practitioners with information about the geometric design of road alignments. At the same time, this document is not just about the road alignments, it's also about the design parameters, about the speed parameters, about the horizontal and vertical geometry. So the design parameters that outline in the guidelines are related to road classification, design speeds, design vehicles, alignment controls, cross-sections components, including traffic lanes, shoulders and verges, and provision for public transport and cyclists. The design parameters include operating speed, desired speed, posted speed, design speed, and their relationship with each other. Horizontal and vertical alignments include development and application of circular curves, superelevation grades, vertical curves, procedures for grading of road alignment, and determination of side distances across vertical curves. You will learn, and I will present during my lectures and outline the various elements that you would need to know and learn about to be able to develop geometric design of major urban roads. The art of the geometric road design, what is it? It is a three-dimensional combination of the elements that establish the road layout, horizontal and vertical geometry, pavement and median widths, crossfalls and superelevations, pavement types, and intersection forms. Prior to talking about the guiding principles for effective 21st century road design process, I want to mention a little bit about the performance-based geometric design process. The typical purpose of the geometric design process is to provide the necessary three-dimensional features for a roadway to address stakeholders' identified problems or needs by providing an appropriate level of mobility and safety improvements for all road users. The traditional philosophical approach to design has been to treat minimum design criteria as adequate to produce acceptable performance. The goal has been to meet these standards or criteria rather than to specifically provide sustainable traffic operations and safety. Some of the dimensions or models have not changed over the decades. The typical updates of the Department of Transport or road agencies' policies and guidelines have been focused on various individual design elements and not on the overall design process. An assessment of the existing design process was undertaken by a range of practitioners to suggest changes to ensure that the recent advances in knowledge and emerging issues are incorporated in the design process. In the recent years, strong stakeholders' interest has emerged. A geometric design process that is responsive to these issues requires measurable transportation or environmental impact terms. This dialogue between design professionals and stakeholders is essential for developing an optimal solution balanced with the transportation and community goals. The transportation knowledge base has grown over the years. Research findings propose that the end goal of the geometric design need to be measured in the metrics of transportation performance, including mobility, accessibility, safety, maintenance, and operations and state of the good repairs. So what are the guiding principles for effective 21st century road design process? There are certain principles that should shape and define an effective process into the future. I characterize these guiding principles in three categories: the fundamental base for road design, the social and public policy framework within which the process is conducted, and the necessary attributes of the effective process. These principles are quite often changed depending on the jurisdiction, but the fundamentals remain. The following slides present what should be the fundamental basis for the design of the major urban roads. Number one, geometric design solution should address objectives and quantitative measures of transportation performance. Number two, social and political framework within which the process is conducted. Number three, necessary attributes of the effective process. So the fundamental principle, number one, geometric design solution should address objectives, quantitative measures of transportation performance. Roadway design projects begin with a stated transportation problem. The purpose of geometric design is to provide the necessary three-dimensional framework of a roadway to address the problem by providing the appropriate level of mobility or safety to the road users. Geometric design involves the application of tools, methods, dimensions, and criteria. Dimensional and other design standards and criteria are a means to an end. The end is transportation performance, and such performance includes, as I mentioned to you already, mobility, accessibility, safety, and state of the good repair. Every phase, sub-process, methodology, model developed and applied to the road design, a road design criteria should be objectively related to one or more measures of transportation performance. The implications of these guiding principles are threefold. First, mentally, you as a designer must shift from a dimensional-based approach to performance-based approach. The traditional philosophical approach to design has been to treat minimum design criteria as adequate to produce an acceptable level of safety. In traditional design practice, roads are implicitly characterized as being either unsafe or acceptably safe, and the application of minimum design standards producing a safe road. This traditional roadway designer's mindset is that of a minimal safety. According to this minimal safety mindset, meeting the minimum criteria is all that is necessary or required of the design. Indeed, the designers are discouraged from providing more than minimum values or dimensions, as doing so is presumed to increase the construction cost while producing no added value. The notion of safety as being a fixed attribute precludes considerations of marginal differences in safety performance associated with a marginally different design solution. To summarize, the minimal safety mindset requires the designers to meet the minimum dimensions, but does not reward or incentivize the designers from using more than the minimum dimensions. The road engineers and designers applying design criteria need to understand not just the criteria, but the basis behind the criteria. This is why this course is very important for you, because on the following lectures, I'm going to present the basis of the design criteria. And despite it may be seen by you as simplistic and obvious, okay, many designers do not understand or not aware about the basis of the design criteria that they're using on a basis of the guidelines or standards that are required by the client to be used for a particular project. The revised design process envisions the designers will need to approach their work with the performance-based mindset rather than the dimensional-based mindset of the design. Their design objective should not be just to apply a minimum criterion, but rather to find the appropriate combination of criteria that provides optional performance for an acceptable implementation cost, such as contribution and cost reflecting the specifics of the content. The second of the threefold implications of the guiding principles is that the geometric design process must be viewed as incorporating continuous change. The advance in our knowledge of safety and operational performance should be routinely input to the geometric design process. The design process should readily and seamlessly adapt to the change in external circumstances. Each project does not exist in a vacuum, but rather contributes to the local, regional, or state transportation network. The design process must be adaptable to the evolution of environmental investment decisions on highways and indeed all transportation infrastructure. The third implication combines the first two. The design process must transition to one that directs the optimization of a solution in the performance-based term within the context of the resources allocated to the road project. This may be viewed as a cost-effectiveness approach, but an important consideration is that the resource allocation should be considered in a life cycle sense. In other words, the design process should directly consider not only the initial capital cost of the project, but also the long-term operational and maintenance cost of the implemented solutions developed by you. Fundamental design principle 2. Geometric design process should explicitly address all potential and legal road users. Road and road corridors are now understood as serving transportation needs, not only for motor vehicle drivers and passengers, including motorcyclists, but also cyclists and pedestrians. The geometric design process should direct the evaluation of the need to provide the transportation service for each of the user type and the spatial and operational design requirements to serve all users. Addressing all legal road users does not merely mean providing space for them within the roadway or right-of-way. It also means designing a corridor in consideration of the unique risk and performance needs of those users, whether it's a bicycle, cyclist, or the pedestrian. In addressing all legal road users, obviously legal who are legally entitled to use your road or major urban road, okay, the design process must provide a means or process for prioritizing what may be conflicting operational needs. Not all roads serve or should serve all road users to the same extent. The context should define what type of users should be expected or explicitly addressed and the relative importance of each type of users. An important aspect of the suggested geometric design process is the recognition of what user type should be included under which context. The third fundamental design principle, the geometric design process should integrate operational solutions with geometric elements. Solutions to performance problems include featuring or concept other than the roadway geometry. Operational solutions include traffic control, signing, and warning devices, travelers' information using intelligent transport systems, ITS, and a real-time demand responsive systems to help regulate speed and relocate signal priorities. Operational solutions are now evolving that incorporate in vehicle technology. The maturation of ITS and ability to operate a corridor or network in real time offers benefits to highway and road agency customers. In other words, the road users, all road users. It all offers opportunity to adjust approaches to geometric design. Fundamental principle number 4. The geometric design process is a forward-looking. Road infrastructure is designed and constructed to accommodate the future transportation needs. Right-of-way purchase for transportation is removed from other productive use. Well-constructed and maintained major urban road or bridge should last for 75 years or more. Right-of-way acquired may be the maximum available into the future, depending on how the adjacent land develops and matures over time. The value and utility of right-of-way will last for 100 years or more. This guiding principle is not new, but its implications are often overlooked by the designers. A forward-looking process contains built-in uncertainty. Actual traffic will differ from travel demand forecast. Unforeseen changes in the context will occur, and road designed, usually models, will not always perform as expected or intended. Such uncertainty cannot be overcome with additional data, greater investment in technology, or more details in engineering. The amounts of uncertainty and the implications of the different features emerging will vary widely based on the local and regional context. The land use in many urban areas is fully built out and stable. Also, certain project types are inherently more uncertain in their outcomes than others. New roads, new major urban roads, or new alignments are clearly the most difficult to forecast the future. The new roads will generally affect the land development patterns in very significant ways. They will change commuting, freight movements, and other travel patterns. Major new roads may significantly impact on regional development in a way that influence the road network beyond the project itself. Safety predictions and operational models based on research elsewhere may be applicable to new roads, but the extent to which actual outcomes mirror modeled ones is inherently uncertain. Reconfigured and reconstructed roads may produce some level of uncertainty in future traffic patterns if they include substantial increased capacity. Such projects may result in intensification of abutting land use and regional travel pattern shift. However, reconfigured and reconstructed major urban roads will generally produce more predictable and less severe changes in traffic patterns than the new roads on the new alignments. Reconstructed roads in their current configuration will generally produce little measurable change in patterns or volume of traffic. Post-construction outcomes will be more predictable from the safety and operational perspective. A significant design process challenge regarding future uncertainty is the conflict between typical nominal design year for infrastructure and usually physical life of such infrastructure. Major urban road projects are sized based on forecast travel demand, which reflects forecast on land use, local and regional socio-economic change, evolution in social trend related to transportation, and national and local policies. Travel forecast typically reflects a minimal 30 years time frame from initial study, which represents a consensus maximum ability to forecast the cumulative effect of the factors that I have mentioned on travel demand. Complex and substantial projects can take up to 10 years or longer from original planning phase to construction. thus frequently resulting in a project size to meet a little as a 20 years future post-construction time. This contrasts with the useful life of a new constructed pavement, bridges, and other infrastructure with at a minimum of 50 years, and depends on many factors that may be as great as 100 years. The geometric design process for the major urban roads must address and reconcile differences in a time frame associated with ability to forecast future demands and needs, and the intent of the infrastructure investment to be more long-term lasting. This is specifically true for the new construction and reconstruction projects. The fundamental principle number 5, design process must be context sensitive to the extent possible and financially sustainable at both program and project level. The geometric design process needs a more robust set of context definers, and design process should support or direct design decisions, dimensions, and choices consistent with the defined context. The 21st century has been the continuation of trends earlier established and emerged of new challenges. The continuation of fuel efficiency placed more permanent limitations on fundings for road improvements. Aging infrastructure became the primary problem facing the various road agencies. Therefore, it was apparent that a new approach should be developed, and in particular, new alternative design concepts should be established. The various Department of Transports and the road agency came under the considerable pressure to explain their programs to explicitly include pedestrian and bicycle infrastructure. The Austroads guidelines are fundamentally a collection of quantitative geometric design criteria and qualitative design guidance that does not present any particular design process. The current geometric design process, with the operational and particular safety effects of geometric design principles, were poorly understood. In the past 25 years, there has been an increasing industry movement towards greater flexibility in design to help projects meet the needs of multiple stakeholders. This flexibility has become easier to justify on a project-by-project basis as knowledge about previously unknown traffic, operational, and safety effects has advanced. As the range of stakeholders' view about road projects and the industry movements towards flexibility has expanded, a number of alternative design concepts have become part of design practice. One of the alternatives is a complete street concept. Another one, concept of context-sensitive design. The third one, concept of performance-based design. Fourth, concept of practical design. Fifth, design metrics approach. Sixth, safety systems approach. Seventh, concept of travel time reliability. And eighth, concept of value engineering. So what is this complete street concept approach. It focuses on creating a roadway and related infrastructure that provides safe travel for all users. The goal to consider all transportation modes in the design of urban roads, including bicycles and pedestrian needs. The complete street concept considers all transportation modes and all travelers. Typical elements: sidewalks, bicycle lanes, shared user paths, designated bus lanes, safe and accessible transit stops, frequent and safety crossings for pedestrians. Concept of context-sensitive design, known as context-sensitive solutions, places priority on assuring that road projects fit the context of the area through which they pass, put projects' needs as well as the values of the Department of Transport or Road Agency and community on a level playing field, and considers all trades-off in decision-making. The goal: to achieve that each project is designed in a manner consistent of roadways, strong community, neighborhood, and the environmental values. Concept of context-sensitive design. It is guided by 4 core principles. Strive towards a shared stakeholder vision to provide a basis for the decision. Demonstrate a comprehensive understanding of the context. Foster continuing communication and collaboration to achieve consensus. Exercise flexibility and creativity to shape effective transportation solutions while preserving and enhancing community and natural environment. Concept of performance-based design incorporates a design process that considers explicit considerations of performance measures, operational and safety performance. The goal: to explicitly consider operation and safety performance measures in the design process to achieve specific operation and/or safety goals. Concept of practical design focuses on addressing only improvements that are needed and eliminates those improvements that are not absolutely essential, reducing the overall cost of the project. Goal: to relax specific design criteria to minimize project cost, consistent with achieving other stated goals. Design metrics approach includes 3 levels of design for road projects: basics, modified, and full level. Goals: to achieve a required level of accuracy in the design details and overall construction cost. Safe systems design takes a holistic approach in that the responsibility for road safety is shared between all facets of the transportation system: infrastructure, roadway users, and the vehicles. Goals: to design each project so that motorists will choose to travel at speed that the designers consider the appropriate to crash risks present on the roadway. The elements of the safe systems approach. Safe roads and roadsides, encouraging appropriate travel speed. Safe speeds, setting speeds that are consistent with the functional classification of the road. For example, if you're driving on a major urban road that is either arterial road or the subarterial road, you would have a certain speed that shouldn't be changing often, okay? If you're driving on the local road, you should have a lower speed, and that speed, again, should not change often. Safer vehicles, vehicles that protect occupants and road users who are being alert and compliant. Concept of travel time reliability focuses on designing a roadway in such a way that maximizes the travel time reliability of the roadway. The goal, to make travel time more consistent and thus reduce day-to-day variations in travel time on given section of road. And travel time reliability, it takes travel time more consistent and thus reduces day-to-day variations in travel time on a given section of a road. Design that can reduce the potential impact of non-concurrent congestions on travel times. Key sources of non-concurrent congestions: traffic incidents, special events, work zones, traffic control devices, such as traffic signals, and obviously weather. Concepts of value engineering. Value engineering is a systematic process of a project review and analysis by a multidisciplinary team to provide recommendations for improving the value and quality of the project. Goal: to improve the value of design by modifying any aspects of the design that would result in an increase in value. Goals are similar to practical design, but potentially seek not only the same or better project performance at lower cost, but also better performance even at the somewhat higher cost. All of these concepts profess to consider a broad range of design issues, but each concept has been advocated by interest groups or adopted by the road agency with a specific priorities in mind. The advocates of each of the alternative concepts, recognizing the need to consider competing viewpoints in the design of the major roads project, and likely consider themselves to be seeking project designs, then consider and balance all competing stakeholder goals and interest, but their choice of the alternative concept may advocate often tells something about the factors to which they assign a high priority. The stated goal of a completed street concept, for example, is to consider all transportation modes in the design of urban and suburban arterials. Most advocates of complete street emphasizes explicit consideration of bicycle and pedestrian needs. The stated goal of the context-sensitive design is to assure that each road project is designed in a manner consistent with the context of the road. Most advocates of the context-sensitive design advocate strong consideration of community, neighborhood, and environmental values. The stated goal of the performance-based design is explicitly consider operations and safety. It's needless to say that all of the alternative concepts have useful features that should be considered in developing a revised geometric design process. Yet none of these concepts by themselves are a complete and sufficient process for identifying and considering all factors relevant to design decisions. Each of these alternative concepts is reviewed and should be reviewed by you as a designer and discussed with a client and seek to seek the most appropriate concept that should be used for geometric design of major road in an area that has been planned by the client. Each of these concepts should be used during development of the performance-based design. Performance-based design incorporates a design process that considers explicit consideration of performance measures, typically operational and safety performance measures. In performance-based design, each design decision should be explicitly assessed in terms of its potential impact on operations and safety. Performance-based design should be consistent with goals identified or set up by a roadway agency of moving away from design for minimal safety, meeting specific geometric design criteria, towards substantive safety, meeting explicit performance criteria. Carried to its logical conclusion, performance-based design could have the goal of meeting specific operational and safety targets established by the road agency for each major road project. A performance-based design process involves, at a minimum, estimating the operational and safety effects of each design decision for which it is feasible to make such estimates with available tools, and so consider those operational and safety estimates explicitly in making geometric design decisions. Typically, many factors other than operations and safety are considered in the geometric design decisions, so the operations and safety will not necessarily be the deciding factors for all geometric design decisions in all projects. But clearly, designers recognize operations and safety as an important decision factors. A performance-based design process with goals based on the both operational and safety targets is now feasible for majority of the major road projects. The current state of practice on CREDI include a performance-based design processes with the goals based on operational targets, such as level of service. And I hope you're familiar with that terminology. If not, I'm sure you'll find out in the various standards. So what is a primary road purpose? The primary purpose of the road is to enable the safe, convenient, effective, and efficient transportation of persons and goods. Roads may serve other purposes, such as moving vehicles, parking vehicles, provision for pedestrians and other non-vehicular traffic, access to abutting properties, access in a case of natural disasters, improved defense capability, improved availability of health, emergency, and other essential community services, and increased potential for a range of economic land use. It should be clearly recognized that roads form but one element of the total transport system, which may include all forms of transport by land, sea, or air. In a properly coordinated and integrated transport system, all appropriate forms of transport should be used for their best or optimum use. Road classifications. In Australia and New Zealand, there are several commonly used type of road classifications: functional, funding, administrative, and road amenity. Functional classification is the most commonly used and classifies roads on mainly arterial, subarterial, collector, local, and the most commonly used. Funding classifications classify roads as a national, state, and local roads depending on the level of government primarily responsible for funding. Administrative classification is adopted by the various road authorities to suit their own particular needs. And road amenity classifications recognizes the requirements of the different road users, truck, cars, pedestrians, cyclists, public transport, and non-traffic functions of the road. On the international level, the hierarchy of the major urban roads accepted today generally falls into the three categories. The category number one, urban freeways. The category number two, urban roads and streets. And the category number three is the traditional streets. As the subject of my lectures are major urban roads, I'd like to define urban areas. They can be defined as developed places within the boundaries set by responsible state and local authorities. Urban areas have fundamentally different characteristics from the rural areas with regard to land use, density of road network, nature of travel patterns, and the way in which these elements are related. I suggest the following definition. The major urban roads are the roads through urban areas serving the major centers of urban activities. They generally have intersections at grade, provide access to abutting properties, and carry traffic in which a greater parts have neither origin nor destination at the abutting property. The term major urban roads excludes streets, collector roads, distributor roads, freeways, motorways, and the expressways. There are two categories of major urban roads: urban arterial roads and the urban subarterial roads. Urban arterial roads are the roads that carry high volumes of through traffic and link the large urban activity centers. The urban subarterial roads that connect are roads that connect arterial roads to the areas of the urban development. You can see this classification on this little sketch, okay? So you can see the arterial roads, major urban arterial roads, subarterial roads, and the collector roads.